We have a resistor circuit problem. So it's like a triangle with 3 resistors. And then it tells you attach a battery on points B and C. So how do you do that? You just do like this. That's your voltage right there. So let's analyze it. This right here, these two, they are in series. Why are they in series? They're in series because they have one flow of connection. Okay, now why is this? Why when it comes to this is parallel. So it's parallel because there is a stop. It's not one direction anymore. You see here, you go, I'm going one direction, and like, oh shit, there's an intersection. I can go here, I can go here, I can go here. It's like, that's a tip on analyzing if it's series or parallel. Let me go to my master guide, which I made. So as you see here, example number 1, series, one flow. This one too, one flow. This one too, the capacitors, one flow. They directly connect to each other, and there aren't any stops, mobile paths, intersections, whatever. Simple. Now we have parallel. You see here, says go, I'm going one way. Oh shit, where do I go? I can go here, I can go here. It's, yeah, basically like that. There's this stop here. Next, example number 2. You see here, the flow, it goes through, and it goes here, it can go here, or you can go here, you go here, best, or just multiple directions. And here, this is the problem I'm about to discuss. So yeah, okay, let's go back. So there's that. Now that we discussed that, let's structure our equations. This is what my teacher taught me, Mr. Medrano. Okay, but we have R1, we have here a series. This is our first equation, R1 plus R2. Because in series, the resistors are added. You can take a look here in the master guide. Then we have our first equation, R1, 2, the combination, is equal to R1 plus R2. Alright, simple. Our next equation that will help us solve the whole thing is we can get our R total, right? So you can get the entire resistance of the entire thing. We have, because remember, we're adding this to this, but this in parallel, so we have here parallel connection. We have here 1 over R1, 2, because this and this, 1 over R1, 2 plus 1 over R3 raised to -1. So yeah, when you have resistors in a parallel connection, you you add them in this manner. So yeah. Next, because we have these equations here, we can derive the equations to help us get our current and our voltage. Our current here, we're just gonna follow the structure here. Remember that currents in series are actually equal to each other. Again, you can refer to the master guide, which is over here. Currents in series are equal to each other. Okay, so I12 is equal to I1 is equal to I2. Next, the second equation, IT is equal to I12 plus I3. So you see here, we're just looking at the subscripts. We're just copying this, copying this, copying this to put here. Okay, so I12 is added with I3 because in parallel connections, currents are added. Alright, next, for our voltage, V12 is equal to V1 plus V2. Voltages in series connections are added. So here, voltage total is actually equal to V12 equals to V3. Yes, so let's solve. R12 equals to our R1, 15, plus our R2, which is 20. That gives us 35 ohms. And now, since we have our R12, we can get our R total, so follow the formula. 1 over 35 plus 1 over 10 raised to negative 1. Our R total is 7.78 ohms. So we write that. Then, as you can see here, a tip here with the structuring of the table. If you see you have two values already, you can get a third one, right? If you have two values already, you get the third one. So, we have our V total and our R total. We can follow the formula, V equals IR. We can get our I total. So that is 10 over 7.78 equal to 1.285 amperes. Okay, what do we do next? So this is the time where we actually try to analyze. What can we do next? So we look at our equations again. We scan through them. You see here actually, we have our voltage. We have our voltage total. That's given. That's 10. Is also equal to our voltage 3 and our voltage 1. Voltage 1 too. Alright, so we can write that. Our voltage 3 is equal to 10 volts. And since we have two values, we can get the third one using the formula V over R. 10 over 10 is equal to 1 ampere. Next, we look here at the table. What do we need? We need our I1, I2, V1, V2. How do we get that? We analyze. We analyze. As you see here, in our equations, I12 is equal to I1 and I2. That solves all our problems, right? So how do we get I12? You see here, we have I12. You can get I12 if you have IT and I3. We have IT and I3. So, let's do that. We isolate I12, we solve for it. IT minus I3, we transpose. It gives you 1.285 minus 1 equals to 0.285. And remember, I12 is equal to I1 equals to I2. So 0.285 is also those. Very neat. Alright. And now because you have that, you're just looking for our V1 and V2, which is simple already. You just use the formula. Let's do it. 15 times 0.285 is equal to what is this? This is equal to 4. Okay. Is this right? Yeah, it is. Okay, 4.275 amperes. That is your V1. And our V2, 20 times 0.285, 5.7 voltage voltage. And yeah, there's that. So what do you need to know? If you want to double check your answer, you look at your series connections. So remember that voltages in series connections are added. When you add the voltages in your series connections, which is this one, 4.275 and 5.7, you realize it should equal to your voltage total. I mean, it's not exact, but it is your voltage. It will add up to your voltage total. So, yeah, that's one way to double check your answer. Thank you.